Okay, so let me start. I mean, going back to this set, I mean, strike, I mean, this set of values, I mean, as Fred pointed out, I mean, the assumption finite rank was superfluous in this lemma. I mean, this is always discrete. I mean, our standard assumptions are now that G is pro P, and omega is a P valuation defining the topology. And so these groups, these groups G by G nu are finite. And this suffices already. So there can be only finitely many values less than u, any given u, and so this means the set is already discrete. So if it is, and moreover, so if G omega is of finite rank, then we know more precisely, and there I murmured something about the monoid generated by it, but this is actually, I got ahead of myself. I mean, this is here plays no role. Later on this comes up, but here it's simply then that this set is of the form, there are finitely many nu, say.
So finite rank means group G is a finite.
Finite rank meant that group G is as a module finally generated over the polynomial ring. S, and then there are finally many of these real numbers, uj, and then you add any non-negative integer. So it's really, I mean, you don't need the monoid. It's equal to the union of such. There was no monoid. The monoid generated by this comes up later. Okay. Now let me, before we go on somehow seriously, let me make another very simple observation, which somehow is crucial for what will follow. So let's assume we have an element. Let's pick an element H, any element. Then we have, of course, the map C goes to G, which sends an integer m to H to the m. So this is a homomorphism, of course. But now since I mean the G nu form a fundamental system of open neighborhoods of the unit element, and this is a P group. So let me call this C, maybe a P group. So it follows that the pre-image of G nu is of the form P to some A u C, right? And so this means that this map is continuous if you give this here the p-adic topology. So this implies C extends continuously to a homomorphism from ZP to G, and which we then continue to denote by this exponential notation. So x goes to h to the x. And surely, I mean, by construction, h to the x is the limit. Say m goes to, I mean, whatever, I goes to infinity, h to the mi, if x is the limit of the mi, the integers mi.
But this is true for any group.
Yeah, I made no assumption here. Sure, sure.
Well, Doesn't need a p-valuation.
It doesn't need a p-valuation. No, of course not. No. I mean, that this is of the form G nu, that didn't play a role. I mean, it's just that the open modular and open, only use that as an open subgroup. And so we can, more generally, we always have, so whenever we fix elements H1 up to Hs in G, then we have the continuous map from Zp to the S into G, which sends x1 up to xs to h1 to the x1 times hs to the xs. Now here, of course, the order matters, right? I mean, order matters. No homomorphism. No homomorphism. And therefore, it maybe at the first sight, in general, no homomorphism. At the first sight, this may seem a useless device. But actually, it is very important. So we make the following definition. In this definition, we need again the p-valuation. So the sequence, or maybe a sequence of elements G1 up to GR in G, and so it's really a sequence. I mean, the order matters. In G is called an ordered basis of the pair G, omega if somehow, if the map, okay, now I used G and here, so I have to write it down again. If the map Cp to the R to G, sending x1 up to xr to g1 x1 gr xr is a bijection, and I write in parentheses, hence a homeomorphism, and satisfies that somehow one can use it to compute the omega in the following sense. So omega of G1 x1 gr xr is the minimum of the omega of the gi plus v of xi. So from now on, okay, so from now on, v denotes the p-adic valuation on QP. Okay, so that's the notion of an ordered basis. Let me also, I need some other notation, standard notation in the theory of graded objects. So if G is an element different from 1 in G, we denote by sigma of G its coset in the graded object, right? So this is the coset of G in where? Omega of G plus. So it lies in gr omega of G called sigma of g, the principal symbol sometimes called. I don't use this language, it's not necessary, but
So did you mean
traditionally
the
it's
order
called the
valuation,
principal.
P-adic valuation?
Sorry?
You mean the order p-adic valuation? The order of an element?
Yes.
Yes.
I mean, the order. I mean, the power of p, which, what do you mean by order?
Ah, you don't mean the, yes, the power of p, with the order of p equals 1.
Yes.
Exactly, the valuation of p is 1.
Power of
Yeah.
p then minus 1.
Yeah. So the additive, if you want the additive p-adic valuation. Okay, this is one notation, and then the following remark before we can somehow start looking at this notion and see that it's useful. One preliminary remark, simple remark. So let 1 different from g in g and maybe x different from 0 in CP, and further let a bar in FP star be the image, right? I mean the unit. I mean this is p to its valuation times the unit. So the unit is then p to the minus v of x times x. So it's a unit, and so it has an image in FP star. And omega g to the x is omega of g plus v of x. And the principal symbol of g to the x so is the principal symbol of g, and then apply to it the simple polynomial a bar times p to the v of x. Right? I mean, there's a polynomial in the polynomial ring, and we can apply to sigma of g. I mean, all you have to show clear from the definitions once we show that omega of g to the x is equal to omega of g for any unit x CP star, because right, I mean this is I mean the p part, this is one of the axioms that then the omega goes up by 1, and similarly of course passing to the p's to a p's power is here the operator p. This is clear. And then the rest is, once we know that the omega doesn't change, we remain here in the same graded p's, and then raising it to the, I mean, then multiplication is the addition here. So, I mean, raising it to a unit becomes multiplication by the image of this unit in FP star. This is all by definitions, once we know this here. But, I mean, this is easy because, I mean, the g omega g, right, where this lies in, is closed. Is a open and hence closed subgroup. And therefore it must also contain g to the x. I mean, whether x is a unit or not, but so this means that omega g to the x can only increase. But on the other hand, if it would be, if we would have a strict inequality, then g to the x would lie in g omega g plus, which is also closed. So it would follow, I can now it's a unit, so I can raise it further to x minus 1, and this would then also lie in g omega g plus, but this is g, and so it's a contradiction. Okay. So having us reassured of this little facts, maybe I state the lemma here. So for any sequence g1 up to gr, g minus 1, the following.
I'm sorry, sorry.
Yes?
So, I don't misunderstand something. I didn't understand the significance of that intermediate step. What are you saying? Dx. I mean, why can't you just say g to the x raised to the x inverse is g, which is greater than
Say
or
G belongs to the subgroup generated by Gx. Therefore, they must be.
Yeah.
But what was the middle thing? I didn't understand.
Which middle thing?
Another way to get the contradiction.
You mean this here?
Right.
No, I mean, I need the contradiction. I mean, if I'm assuming, yeah, I mean.
Oh, okay. Okay.
Yeah.
You didn't need a contradiction. Yeah.
And then what he means is from the second line now G is also Gx to the x to the minus 1. Therefore, it's greater or equal to Gx.
You can just say
the
from
second
there,
line.
just from the second line. Omega g to the x.
Ah, okay. You mean
Okay, you have another inequality.
yeah, you are right. You're right. That's right. Okay. Yeah, sure.
Avoid proofs by contradiction.
Okay. I keep my comment to myself, Mignon. But you're right. I mean, sure, absolutely. So the following assertions are equivalent. So first, the elements, so the principal symbol, I mean, this element sigma of the sequence in G are linearly independent over the polynomial ring. Second, we do have somehow the formula in this definition up there for products, for such products. I mean, so we have that omega g1 x1 grxr is equal for any and thirdly, and somehow very important, I mean, right? I mean, it looks as if, I mean, since the group is not commutative, it looks as if even if you have this formula above there, it does not allow you somehow to compute the omega of a product. And that's not true, actually. I mean, in some sense, from the omega point of view, the thing is commutative. So if I have, if I have two such elements which can be written as, so if G is, say, G1 x1, GR xr, and H is G1, Y1 up to GR, YR, then I simply have here the minimum plus, so which is the V of, I think it's yi minus xi. Is it? Which was the yeah, it doesn't matter. I mean, okay, it doesn't matter. I've written here differently, but of course it doesn't matter in which order I write it. Okay.
So the second condition is x1 to xr, to
CP to the R, any p-adic integers. Okay. So, okay. Move. So let's start with 1 implies 2. So we certainly have, right, axiom. I mean, maybe I should slowly stop to mention axioms explicitly, but and the remark we have certainly that we have an inequality here. Right? I mean, the product, taking the product apart gives bigger or equal to the minima of these, and then by the remark we know those as such. So we have omega G1, X1, and so on. Okay, so let me, yeah?
Okay.
Sorry?
Are you sure that this last thing is okay?
How?
If G equals 8, then the right side still makes sense, but the left side is not defined.
What? I mean, then this is 0, so it's infinity, and this is also infinity.
No. But you say minimum.
Yeah, but the minimum of infinity and infinity is infinity.
How is it?
So let me denote this number by nu. And so let's suppose, I'm very sorry, Mignon, but I do this again by contradiction. So suppose,
Okay, as long as you don't contradict yourself.
yeah, I mean, of course, this can happen all the time, who knows? So let's assume this lies in G nu plus, right? I mean, that's what we want to exclude. And so now let me actually take, of course, they may be different here, these numbers, but some of them are equal to nu. So let me single them out. So let I1 up to IS be those where omega gi, those I, where omega gi plus v xi is equal to nu. So there is at least one. But then already the product of those gi 1 up xi1 up to gis xis lies in g nu plus. And the other factors, the individual factors, lie in there then, because they have strictly bigger omega, and because this is normal, right? G nu normal in G. Even if they sit somewhere in the middle, they disappear, modulo G nu plus. So now you see now the advantage is now they all have the same omega, which is equal to nu. So therefore this product corresponds to the addition in the graded piece. So it follows that sigma of the sum of the is 0 in Gr nu G. But I mean, right? I mean, this is now by the remark. Maybe I don't have to write this down explicitly. I think by the remark A2, this is a non-trivial linear relation. But they were linearly independent, so it's a contradiction.
The remark was where you wrote these symbols in terms
Right.
of
Exactly. The second half of the remark, we could write these as applying certain polynomials to the original sigma of G.
So can be without contradiction.
I'm sure it can, yeah.
You just write nu and look at this.
Yeah, sure, whatever. I mean, okay, so the reverse. So now let's assume we have so consider any relation in Gr. So, right, I mean, we have polynomials qi of p applied to sigma g1 and so on. Qr of p applied to sigma of gr is equal to 0. Now, let's assume, so we have to write out the polynomials. So let's assume qi of p is the sum j aij bar p to the g. And where I write this is indicated, is supposed to be indicated by, so with integers aij in z, and the bar means then the image in fp. Bar is image in. And let me also denote, let ui be the omega of the gi. And then if you unravel the definitions, then this means, this relation means the following. So of course we have the sum over here the sum of I equal 1 to r, and then the sum over the j, gi to the aij times p to the j. So it's still an expression in the graded. I mean, I write this out somehow explicitly, but still in Gr of G. nu I plus j plus is 0. So this is still in GR of G. Right? I mean, I have just I mean, this means applying, I mean, in this polynomial, this means applying p, and then the degree goes up by 1, so the j has to match here, this here. And then the rest, the coefficients, just also means in the corresponding GR, also means actually raising to the corresponding power. Right? I mean, if they are non-zero, then this, if this is non-zero, then this is really non-divisible by p, and otherwise it disappears in there, because I have here the degree is only determined by this exponent. If this further is divisible by p, this means the coefficient is 0, then this is also 0. This coset is also the trivial coset. So now let me, for given u, let us collect the terms in nu. Right? I mean, they have this being 0 means in each homogeneous part it has to be 0. So if I have collected terms in a fixed homogeneous part, it's still 0. So I get, and then I can, of course, in a fixed homogeneous part, the sum here in the GR becomes in the group just the product. So it means I have the following. Let's see whether this is correct. Gi ai u minus ui times p to the nu minus ui is in G nu plus, where with the convention that u minus a I nu minus nu I is 0 if nu minus nu I is strictly negative. Right? I mean, if I fix my nu, then I have to look here at these equal to nu. This already means at most 1j can, if I fix I, at most 1j can contribute. And I mean, it contributes as long as if this does not happen. I mean, right? I mean, otherwise there can't be any j. And then, of course, this j becomes the nu minus nu I up there. Actually, it's not true. I have to write, I mean, of course, the difference, maybe it's not an integer. I have to write if nu minus nu I is not a non-negative integer. Right? Only if the difference between u and one of those here is a integer bigger or equal to 0, this actually occurs. This contributes a factor. Okay, but now we have, by our assumption 2i, right? I mean, we can compute the omega of this here. Omega of this product, the above product, is equal to the minimum of the I, and then the omega gi, and then the p-adic valuation of those, so plus nu minus nu I plus v of ai nu minus nu I. Now, but I mean, the new i's were exactly the omega of the gi's. So they disappear. And this here disappears. And the assumption was that this lies in here, so this is strictly bigger than u. And so this means, I mean, all the, right, I mean, I have a u here, this is strictly bigger than u, so this means so it follows then that all these a's are divisible by p, and so modulo p, the a bars, are 0. And so if I do this for any nu, I get that, so for any nu, it follows that all the coefficients are 0. Okay. So this is this direction. Then of course the 3i to 2i is trivial. So maybe I'll write this here, 3i to 2i is trivial. So it remains to show 2i implies 3i. So again, let me denote the right-hand side by nu. So put nu is the minimum omega. And then remember that we call G nu modulo G nu plus is central in G nu. And so now we can do the following, following computation. And I mean, let's compute this coset. Now, I mean, we insert the definitions first. Of G and H. Sorry, G1 up to GR X. Sorry, the order of course reverses also. R1, 1. R. Now here we have this already in the correct. Here I can replace this in the middle. I can replace. So here comes G2 minus Y2, and this I can write already as X1 minus Y1, G2 X2. GR XR. And now, thank you. And now, I mean, this thing here has omega of this is at least nu, right? So it lies in here. It may be the zero coset, but the trivial coset, who cares? It lies in here, so it commutes with the others. I can shift it, for example, to the beginning, right? So I can shift it. And then I have the next pair, which is okay. So I can repeatedly apply this principle, and in the end, they are there in the correct order. Right, and now I apply simply, so 2i tells me then that, I mean, at first I get that omega of g minus 1 is omega of this product here. This product times an element k with omega of k is strictly bigger than nu. But on the other hand, by assumption, right, by 2i, I know that this product here has omega equal to this here, which was nu. So omega of product is nu, which is strictly less than this one, and therefore this here is equal to the minimum of the two, so to the product, the omega of the product. So that's it. Okay, so now we can sharpen this in the following way. Proposition. I think I want it. No, not here. Okay. Now let me assume that the thing is of finite rank, although, I mean, I will come back to this at the end. I mean, here we didn't make the assumption, right? So now let's suppose if g omega is of finite rank, then for any sequence the following are equivalent. First, this is an ordered basis. And second, the sigma of the GI is a FP P basis of GRO G.
So in the end, the order doesn't count. 2 is independent.
That's right. I mean, to write down, of course, this you still need. I mean, yeah, that's right. I mean, if it's in a basis in one order, it's a basis in the other order, in any other order. Still, the map, of course, right? I mean, is different. Yeah. So I to I. So we know, of course, already, so the lemma tells us already that they are linearly independent. GI are linearly independent. Okay, so now we have to show that they generate everything. So it's of course sufficient to show this for homogeneous elements, that they get any. So need to show that any sigma of G is a combination of the sigma of gi. Now by I we can write our g as g1 x1 gr xr, and so again, of course, I mean the factors can have different omegas. So again, I have to pick out only those which have the minimal one contribute. So let I1 up to is be those I where, right? I mean we do know that omega of g is the minimum of the omegas of the factors. So where, and we single out those where this is where the minimum is attained. So omega of gi xi. And then as before, I mean the others to the sigma, the others do not contribute. So then sigma of g is sigma of gi1 up to xi1 gis xis. Right? I mean this was the same argument as in the previous proof. And now I'm everywhere in here. All the factors have the same omega. So they all lie in the same homogeneous component, and there the product is the addition. So this is sigma of gi1 xi1 plus sigma gis xis, and this is then the rest is again this remark. Right? I mean now I can write this as applying a polynomial to even a monomial to sigma of the g remark. A2 gives me the relation. So I mean, right? I mean again applying the lemma. I mean, we do already know that then for elements in this form, they have the omega has the correct value which we want. So we only need to show, so by lemma 8(3) need only to show that any g in G is of the form Gi, Xi, and so on. Now remember that this map from this was continuous, so the image and so let maybe capital X be the image. I mean the set of all these products. Now it is as the image of a compact set under continuous map, it is closed in G. So I want to show that it's equal to G. I need only to show that it's dense in G. So need only to show that any G in G lies in X modulo any neighborhood of the unit element, modulo any G nu. Okay, and okay, I need space for that. This is an approximation argument. By the way, maybe I should say, I can make the remark already now instead of at the end of the proof. I mean, see that in this part of the proof, we have not used that the group, that G omega was of finite rank. It was not used. So you see this, so in other words, this also gives a means so in other words, once we have an ordered basis, we do know that the group is of finite rank. I mean, as the proposition is formulated, it seems as I would have to know this in advance. But for this part of the proof, we didn't need it. So, I mean, this I could have formed, this implication I could have formulated without assuming already that G omega is of finite rank.
So this map represents the exponent to the thing.
Yes.
So it's obviously injective.
I mean, why do you care?
Because to be a G basis, to be an ordered basis, you're supposed to get a bijection, right?
No, but okay, but this follows, of course, from this formula here that it's injective, right? I mean, maybe. Wait a minute. I want to show that it's an ordered basis. No, I mean I need this formula. I need this formula, right? I mean injectivity follows from this formula. If two go to the same element, this is one, and so they have to be.
Remember the definition of what is an ordered basis. You didn't really say anything that it should have something to do with G. It's the set of all the elements of the form G1 to the R1, GR to the XR. You did not say that actually should be somehow in G.
What?
Yeah, yeah.
I don't understand.
Consider the RPG as a bijection.
That's it. But then it could be very well be that actually the subgroup generated by G1 to GI is a proper subgroup of GI.
No,
It's a bijection. It says in particular any element in G is a product of G, is of this form.
Bijection on the image. Usually when you say bijection.
No.
No, I mean a bijection between two sets. I mean, yeah.
Good exam question.
Okay, so
The Americans can make it a bijection on.
okay, I'm not an American, so I'm excused. Okay, so we have to do this approximation. So step one. So we can write our sigma g, I mean using 2i, right? 2i follows, we can write sigma g as a linear combination. And but I mean this is all a graded thing. So if you compare degrees, then you see the following. Right? I mean, we control exactly the degrees. I mean, if you apply a power of p, the degree of this goes up by the corresponding exponent. That's all what happens. And this sits in a specific degree. So this summand only can contribute something. I mean, if there is in this polynomial, there is a monomial of where the exponent is the difference of these degrees here. And only this one matters. All the others, I can omit them. This in each summand. So I can write this in the following way. There is a sequence. I mean, a subsequence here. Maybe some of them do not contribute anything. They cancel out anyway. So I again have such a sequence And now, of course, yeah, IS and units A1 up to AS, CP star, again with images, right, my bar notation, AIJ in FP star, such that all differences, I mean, so that this can contribute to here at all, and the difference of the degrees must be a non-negative integer. J is a non-negative integer, and sigma of G then is A1 bar P to the omega G minus omega G A1 applied to sigma G1 plus and so on. AI1. No, here I don't need double indices. A S bar P to the omega G omega I S applied to sigma of G I S. But we do know, right? I mean, again, maybe by this previous remark or whatever, this is the same as sigma of a product G I1 X I1 up to G I S X I S with X I J is defined to be A J times P, small prime P, omega G minus omega G I J. We simply, and this was the previous remark, I mean, you know what the sigma of this is, applying such a monomial. So, hence, we have found, say, this element G may be upper 1. So this product, GI1, XI1, GIS, XIS, it lies in capital X, such that G, did I give this a name already? Oh no, I don't write it. I mean omega G plus is equal to G1 G omega G plus. In addition, it's important, again, all these factors have the same omega. In addition, we have omega G is of course omega G1, this is clear, but it's also equal to omega Gij Xij. Right? I mean, this is the way this was constructed. I mean, here, the omega goes up exactly by this difference, so I end up with omega j for each factor. Okay, so now step 2. So write G is G1 times H with now omega of H is of course strictly bigger than omega of G. I mean, if H is 1, yeah, we are finished. If H is 1, finished. I mean, I'm not sure whether I formally have to distinguish it, but it makes it clearer maybe. So otherwise, apply step 1 apply step 1 to H. So, and obtain H1 in X such that, I mean, I want to somehow, I mean, let a little space if you copy this down, because, so, I mean, strictly speaking, we have this here, right? Equal to H1 G omega H plus. But let me multiply this right away with G1. Then I have here G omega H plus. But now you see, now we use this additional property plus our all centrality statement. I mean, for the H's, let's say, which means now, because they all have the factors of H1, they all lie in G omega H, right? By this additional property, so I can modulo G omega H plus. I can commute them with any other. So this means I can. This is a product of two elements in X. But by this remark, I can again somehow reverse the orders, and I get that this is again an element in X. So I can write it as yeah. I mean this is G1 H1 is of the form G2. I mean, this lies in G2 times G omega plus, where with G2 is in X. Okay, and now you go on, right? I mean, right? I mean, so we have now G is equal to G2 times something of omega strictly bigger than omega H. They are equal, we are finished, and so on. So go on. I mean, deductively. And since the value set of omega is discrete, set of omega is discrete after finally many steps, I mean, we are bigger than any given U. We are bigger than, I mean, any given U. Right? And so this means we can approximate our element G modulo any G in U. That's what we wanted by elements in X. So they are X is dense, and therefore it's everything. Okay, I guess I have to stop. I've not quite managed to do what I wanted to do, but okay. Thank you.